Okay. You know, the cool thing about this course is once you come up for the preliminary examination, you'll be able to go back and review this course by playing all the YouTube videos at double speed, right? And then you can slow them down when you want to. So that's kind of nice. So let's go ahead and get started. I guess the first thing we want to do is a little bit of my wife doesn't like these glasses. She says it makes me look too nerdy. I also have some other glasses, but they hurt my nose. So I wear these glasses. I hope you're not offended. And I'm a nerdy guy though, so I should look nerdy, right? Let me go ahead and share my screen here. And as usual, I got 1,000 windows open. It's hard to keep your heating bill down when you keep all of the windows open. Okay. Anybody figure these out, by the way? The imponderables at the end are turtles deaf?
Yeah. They don't have ear structures, but they do have hearing.
Okay, so I should put, do turtles have ears? That would probably be a better thing, right? Okay, so let me change that. Do turtles have ears? Okay, are honeybees deaf?
So that's another kind of answer. They don't really hear, but they can sense vibrations with their hair.
Oh, I can sense
antennae.
I can sense vibrations with my hair too, but I wouldn't call that hearing. I don't know.
Well, they do use it to communicate, though.
Okay. Oh, okay. Okay. Well, that's good. My wife and I do that. She rubs my head and I rub hers and we communicate. Okay. Are Chinese chopsticks longer than Japanese chopsticks?
Think about restaurants that I've been to. I think so.
Yeah, I forget which one, but one of them is longer than the other one. One of them is longer than the other one. And I did tell you about the Chinese diet. If you want to lose weight and you live in China or Japan, they just take away one of your chopsticks. Okay, that's funny. We can't hear people laugh, but you know what I should do? I should get a laugh track. And every time I tell a joke, I should hit, like they do on situation comedies where they tell this joke and everybody just laughs. I need one of those. Okay, let's go through these. Let's do the game of tic-tac-toe, first of all. That one kind of interests me. I think the people that tackled this last time were Glauco and Adam. Do either of you have a more definitive answer, or did you, like I, think this is a stupid waste of time to spend solving and just give up?
I put my solution in an Excel, colorful Excel, so I can show it to you.
Okay, let's show it to them. And everybody, let's try to break Glauco's spirit.
Do you have to enable?
Oh, I'm sorry. I have to enable screen sharing. Isn't this interesting, though, that you can actually visualize stuff in 4 dimensions? It's kind of interesting. I think it is. 4 spatial dimensions. Okay, here we go. What's in the middle?
In the middle, you can plug in anything you want without a winning combination.
Oh, really? Okay.
Yeah.
Okay, everybody, let's take a look here. Yeah. Okay, everybody's trying to crack your encryption here.
I can do tell you the argument why I think this is correct.
Okay, let us look just a little bit longer. Okay. Just humor us, if you will. Okay. Wow, did you think this was easier than the 3-dimensional case?
I didn't look to the 3-dimensional case. I just tried something easy to solve this problem, and it worked.
Oh, okay, okay. So you came up with an algorithm. This is really cool because you came up with an algorithm to perform this operation, right?
Right.
Okay. Okay, tell us your reasoning behind here about the visualizing stuff in 4 dimensions, 4 spatial dimensions, just like Flatland. Remember Flatland? That 2-dimensional guy wanted to see stuff in 4 dimensions, and the 3-dimensional guy said, "Nope, you can't do that. That's what we have here."
Yes.
Go ahead.
Okay, so let me try to speak in the dimensional sense. All the winning combinations, they need a continuity with the same sign. So I tried to break the continuity. So you see in the borders, there is only one line, and together there is only one line. So you break the continuity with the X here.
Okay, in the middle, you broke that continuity. Yep, I see that.
And then I break the continuity here in the middle. So you can have, I have breaks in the middle of the continuity, here and here, and then for the borders, I have 2 things together that they are only 1 point wide. So they cannot, you cannot put the winning combination. And the same with the diagonals. I have just one here, and so you can, that's the idea, and it seems to work. So
Yeah, the whole idea, I think that's the way I found the tie in 3-dimensional tic-tac-toe, is I tried to break the continuity. That's something that you want to do. Okay, does anybody see a winning combination, or are you convinced that Glauco is right by your engineering proof? I think that you have broken all the continuity. Is that right?
I think so.
Okay, well, let's congratulate Glauco. How do we give him a hand clap when we're on mute?
There is a button here in the chat, but
Unmute.
Okay, that's good. That's good. Okay, well, very good. Thank you. That was enlightening. Could you send that to me and I will make you famous? Well, not famous, but could you send that to me, Glauco, please?
I will send it to you. I was
okay.
Sorry.
Thank you. Thank you. Okay. Let's see. Did anybody get 51? Let's do a random selection. And let me get out my little Das Buch here. I took German all of my life. I took it in high school. I took it in college, and I hated it. And the only thing I remember is Guten Tag, Luise, wie geht's? Wie heißt du? That's all I remember. That was the first dialogue of my first lesson. And it used to be that you had to take foreign languages because when I was a boy, all of the great literature was written in either German or Russian. And in order to understand the great literature of the world in engineering, you had to speak Russian or German. Well, since then, since IEEE is the dominant society in the world, IEEE is the largest society in the world with over almost 500,000 members. I think, it's over 400,000. I do know that. And they have a policy that anywhere in the world that they hold a meeting, that meeting must be given in English. So I've never had the need to use my German. So. I remember about the neuters. I remember that the book is neutral, das Buch. I wonder what they're doing with all this politically correct stuff. Do they have to have politically correct pronouns in German now? Yeah, I don't know either. Okay. So let me go ahead. I got to watch out. I have motor mouth today, and I don't want to detract us from the things at hand. Okay, we have a very nice quarter. Ooh, I don't like that quarter because the heads are ambiguous. I don't like coins with ambiguous heads. Okay, so we have a very nice Queen Elizabeth dollar from, I think, Australia. Okay, right there, Australian coin. And then an American nickel and an American penny. The American nickel looks to be old. It looks to be, I dropped my Australia. Okay, I'm not going to look anymore. Anyway, it's old because it has the Monticello in the background. Okay, do you remember your numbers from last time? Okay. Okay, here we go. Glauco, you're 0. David, you're 1. You've advanced in the world. David is usually 0. Adam, you are 2. Aiden, you are 3. Chris is 4. And somebody is not on my screen. That would be Justin, you're 5. Okay? Dum, 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 dum. Tails, tails, tails. 0, Glauco.
Okay.
If you didn't do it or you're embarrassed in your answer, just say it.
51. I think we had done the A part.
No, I don't think we did. Oh yes, we did do that. Yes, we wanted to do the B part. Yeah, you're right.
So the B, I can show it to you. I think the coefficients are not correctly computed, but I can show you my work anyway.
Okay, on a scale of 1 to 10, how certain are you of your results?
Apart from the coefficients, I think the other part can be right.
Okay.
So 5.
If I was a lawyer, I would say, Glauco, you didn't answer the question, but that's okay. Go ahead.
A 6, more 6.
Okay, 6. Okay, it's above 5. That's enough to win in a civil case. In a civil case, you just have to show preponderance of evidence.
Okay.
So you would win. You would get credit for your homework in a civil case. Go ahead. Oh, I have to stop sharing, don't I? Okay.
Okay, I'm going to share the screen. So I have the hexagons here. These are my vectors, P1 and P2. So they are 1 square root of 3 and 2, 0. So I compute the matrices and I get here, not here. So in order to do the hexagon, I draw an hexagon here.
Yeah, I see that. That's right. No, that's great. In one of my papers, I ran out of Greek letters, so I started using Russian letters and then Hebrew letters. And this is neat because you're using a letter that nobody knows about. Okay, so hexagon.
Okay.
Is that the same as a hink?
Hink is the transform.
Oh, I see. Okay. Okay.
It says hint, but it's hink. This is a mistake.
Okay.
So I have the hexagon minus the circle in the middle.
Yes.
So I did the Fourier transform. And these coefficients, I'm not sure this is right.
No, I don't think that's right. I don't think that's right because what you want to do is you want to have the samples be the hink at QM, not at M.
At QM. Okay.
Yeah, I think so. That's where you want to sample it. Did anybody get something which is better than this? Okay, Adam, go for it. Oh, big mistake. Okay.
That is. So yeah, trying to redeem myself from last time when I was wrong on it.
Oh, okay. Good, good. Yes. Oh, that looks a lot better.
Right. So yeah. So same thing. We assume we have the hexagon function here, which transforms into the hink.
Yes.
And then we plug in QM here, and we do just like we did before. The circle is still over here the same with the 2 jink.
Yeah.
And then we turn it into the S.
Yeah. See, Glauco, what you assumed is that there was a rectangular sampling in yours. You assumed a rectangular sampling. The sampling was not rectangular, it was hexagonal. And Adam's notation captures that hexagonal sort of sampling. Okay? So, good. Adam, you are redeemed. So, this is good. Okay, thank you. Go ahead and unshare your screen. Okay, let's... this is really interesting. Okay, let's go ahead and do the next one. Okay, David, you had a comment, editorial or otherwise?
I was wondering, why do we have the transform of the shape of the brick or tile, or the difference between the transform of the tile and the shape of the, and the function that's sampled within it, with just some random magnitude, relative magnitude between them.
I totally don't understand your question. I'm sorry.
I think what I did was I assumed that the tile had a value of 1 and that the circle had a value of 0. That's an assumption we made in an example, and the problem does not specify the magnitudes. So I just went ahead with that assumption, and that is why I had the tile minus the circle.
I guess, yeah, why would there be any term for the shape of the tile if if what's outside of the function has magnitude 0?
Well, one of the problems that we have is that we have to use a tile that totally subsumes the circle. Otherwise, if you use like a rectangular tile, that rectangle would break up the circle into different parts. Remember we talked about that last time?
Yeah, but I mean, why would the why does the hex and the hink show up at all if the circle is completely subsumed?
Because we have to determine, well, the rectangle, if we arrange the circles maximally packed in a hexagonal sort of fashion, that necessitates the choice of the hexagon as the only tile which totally includes the circle. You can choose other tiles, but if you choose other tiles, it breaks up the circle, doesn't it? And since you are going to have to Fourier transform over a single tile, you want to choose a tile where the Fourier transformation is the most simple. And the most simple is to use the hexagon.
Yeah, but why does it make a difference that, like, we use a hexagonal tile rather than a like something that is drawn around the outside of the circle and into the like maybe a drop-shaped tile? Because if the magnitude of what's outside the hexagon, outside the circle is 0, why
Yeah,
should...
but outside the circle, that's only in a single tile. You have to take into account the entire periodic replication. And with the entire periodic replication, what's outside of the circle is not 0, or what's out, it's not a constant. What we're talking about is taking a single period, a single tile, and doing the Fourier transform of that. So let's move on. If you have a question of that, we can meet after class, okay? Okay, let's try this. The Fourier transform in figure 6.84. Let's try to do this quickly, and I will now choose an appropriate person using, can you see me? Okay, good for you.
Dr. Marks,
What's that?
last class meeting, you said that I would do the hexagon because I said that I had a decent answer.
Okay, go for it, Aiden. Yes, okay.
Okay.
Yeah, I want to see how you did that, because there's a bunch of ways to do it, and it's very interesting.
Yeah, so I can share once you stop sharing. But
okay, sorry. Yep, I'll do that. I am stopped sharing.
So it's been almost 10 days since I did this.
Okay.
But I thought it was due last week on Tuesday, so I
Yeah.
haven't done it since like last Monday. But there's going to be a lot of geometry that I did that I'm not going to be able to really explain, but at least I can describe my approach and it won't take too long.
Okay. Yeah. Just overview it. Okay. So you
Yeah,
did.
so I did break it up into like 3 diamonds, and so I had 3 different functions basically, and I just did them all separately, and at the end you would have to combine them.
Okay. Show me the diamonds though. I only see 2 diamonds. I see.
There's 1 here, 2, and 3.
Yeah, 2 and 3 do a diamond, but what's left is not a diamond. I don't see how you break it up.
So you're saying 2 and 3 should be diamonds, but 1 is not?
Well, I see a diamond on the left.
Yeah, but that's just number 1. The hexagon is made up of the 3 diamonds shown here.
I don't see 3 diamonds. Anybody else see 3 diamonds?
Yeah, rotated. So
Yeah, it's 3 rotated diamonds. Yeah.
Yeah, they're rotated. 2
Oh,
and
okay.
3 are rotated.
Okay. They're parallelograms. If you rotate it, it's okay. Yes. Okay.
Yeah, it's just a rotated diamond. Yeah, yeah.
Okay. Yes.
So basically, diamond 1 is a real diamond, so to speak. It's only rotated by 45 degrees. It's scaled and it's shifted along T1. Diamond 2, I rotated it by 45, then scaled it, and then rotated it to get into the correct orientation. And I shifted it along T1 and T2 to get to this position. And then the third one, I rotated, scaled. Basically, the reason why I rotated twice is because I knew that rotating 45 degrees, then scaling each one the same way would give me the exact shape. But if I rotated it all the way to where it should be, I didn't know if scaling would be the same. I didn't think it would, so I just did it. I rotated every single one by 45 degrees, then scaled it. And then from there, I rotated it more if it needed to be rotated, or I shifted it, and then I shifted it.
I see.
So basically, like for example, the first function is the simplest one. I rotate it by 45 degrees, and then I had to calculate the shifting coefficients. How I actually got those, I don't really remember, but I had to calculate the geometry of the diamond. I know that for sure. And then I had to shift it by a certain amount. This is the, I don't know what you'd call it, the radius. It's not really the radius, but it's this value here, and that's how much it shifted. So I know the shift is correct here.
Okay.
And I had to make sure I did the matrices in the right way. So this should be rotating, then shifting, or scaling based on what we did in class.
Right.
And so I did the determinant of A, or one of the determinant of A, because that has to be multiplied on the front. And I did the transpose of A and then multiply it times U, the U vector. And then I actually didn't write the original function down and then T, but it should be a square, which transforms into a sinc. And then I have an exponential here because of the shift.
Yes.
And that's the first one. The second one, like I said, I rotated and scaled it in the same way, but then I rotated another 60 degrees to get it into the right orientation. I calculated that somehow over here. Like I said, I don't really remember how I did it. And then I had to do a bunch of geometry to calculate the correct shifts to get it where it's supposed to be. And then what I realized is that the third function is just this one, the second, but transposed over T1.
Oh, it is, isn't it? Yes.
So I just did for the third one, I just had the same matrices set up as I did for the second function, but then I just transposed at the end.
Right.
So the whole operation is rotate, scale to get it into the correct general shape, and then rotate it again to get it into the right orientation, and then just transpose it so that's flipped over T1. And that transpose matrix should be like this. That's what I calculated. And then again, I calculated A, got all that. That's the function 3, and at the end, you just add them all together to give you the.
Excellent. Yeah, I didn't follow all the numbers, Aiden, but it sure looks like you did exactly the right thing. So.
Yeah, that was the hardest part, was geometry. I didn't really feel like writing or drawing so many shapes over and over again, so I just tried to do it in my head as best as I could.
Okay. I don't know. You know, I've always been the type, when I do mathematics, I used to get big sheets of paper and just waste them all over the place. Now I go through this and I have all my calculations in here, and I would work a problem, then I need to work it over just in case I made a mistake and work it over again. And that's just the way it is. The older I get, the more I have to work it over before I get it right. Okay, excellent result. Thank you, Aiden. Let's go back to the sharing here. Anybody else want to? I think that the rest of these are fairly straightforward. Did anybody have any questions on them? On any of the shapes that you did? If you do, I won't call on you to do them, but we will do them. So you think if I ask you this in an oral exam, you could whip it out? Okay, I got an affirmative nod and a shrug from Adam. Okay, a hand waving, I don't know. Okay, so let's go ahead and skip that, because I do want to make sure that I finish the POCS sort of thing. A signal x of t, okay, this is the one where you have a spectrum of an equilateral triangle in B, and what's a sampling matrix? You can use to minimize the sampling distance. Now, this is a problem where I don't know, I never got a definitive answer that I proved was minimum. I don't know if you can prove that it's minimum. If you prove that it's minimum, I will be very impressed. So this is tails, 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 Glauco. No, we had you already, didn't we? I think I'm using unfair coins. Heads, tails, tails, that's 4. Who's 4? Chris?
That's me, but I haven't done this yet.
Oh, you haven't done that?
So, yeah.
Okay, okay, let's try another one. Tails, heads, tails, that's 2.
That's me. Can you unshare?
I can do all things through Christ who strengtheneth me. Okay.
All right, so unfortunately, I did not prove that this is the best one. Through a formal proof, I kind of did some geometry in my head and convinced myself it's the best.
Yeah, that's about what I got too. Yeah.
But yeah, so basically the shaping of it is you have your triangles, and then halfway up the triangle, you start the other triangle. And if you kind of look at the square that would fit one triangle, which would be the kind of the default method of doing it, is just have all the equilateral triangles in a B length square. Then you notice that it brings in this part of this triangle, this part of this triangle, which both of those are about 1/8 of a triangle. Well, they're not about, they're exactly 1/8 of the triangle. So that reduces the amount of white space you would have otherwise, because otherwise the amount of white space you'd have with just tessellating it.
No, I don't think you could use the square, because you can't have any redundancy in the triangle.
Exactly. If you use the square, then half of your space is blank. Yes. The upside down triangles would be empty.
Okay, so
I'm saying that would be the default approach, that this is better than. But I guess anyway, I'll answer the problem first.
Okay, let me ask you here that could you trace with your cursor what you think a tile would look like? This is an interesting problem, because it's not apparent to me what a tile would look like here.
Oh, I see what you're saying. I think. No, that wouldn't work here. No.
Yeah, so a tile, I don't think, this is the first time I've thought about it, but I don't think you can get a tile that just contains a simple triangle. I think you have to bleed over other parts of other parts of neighboring triangles into the tile in order to get the periodic replication.
Yeah, but I don't see what shape you cut out to make it work either, though.
Well, first of all, I think you can see that it's hexagonal, right?
Yeah. Mm-hmm.
And I think that if you make a hexagon and Yeah, well, I think clearly a hexagon would do it, correct? And the question is, what is that hexagon?
Mm-hmm.
And always look at the periodicity vector. If you drew a periodicity vector there, say from the triangle, the middle of the triangle to the middle of another triangle. No, okay, yeah, there, and then another yeah, and you completed that parallelogram, you would get a tile. Don't forget the default is always completing the periodicity vectors with a parallelogram. That's always a tile, always. And so we could have that, but again, I don't think that there's any way that we can get a clean triangle out here.
I think you can. You have the triangle and then the two empty small triangles that are on its upper right side.
No, you can't do that. If you have the whole triangle in it, you cannot use another part of the triangle. No, that won't work. That won't work.
No, but David is, I think he's saying taking a triangle and two empty spaces.
Yeah.
Without any other part of any other triangle.
Okay.
Just one triangle. Yeah.
Kind of an hourglass shape.
No, an hourglass shape would not be a tile, would it?
I think it will.
Yeah, I think it would.
What do you mean by that it's not a tile?
Yeah, I don't think it is a tile. I think this is something for you to think about. This is a good question for me to ask in your final as to what is the tile here, or what is a tile. Go ahead, Justin.
I mean, isn't the tile just anything that can be replicated?
Yes.
Okay, so the hourglass would be able to be replicated. It's the triangle plus the top two empty spaces, is what they're saying. You could then replicate that.
Okay, I'm not seeing that. Does anybody have the capability of drawing this for me?
You want me to pull up Paint? Is that what?
Yeah, give it a try. Sure.
Okay.
I'll try it real quick, and if you get a better one, we can look at yours.
Okay, so Adam is going to complete this.
That shape.
You're not sharing your screen of your Paint. I think you just shared your PDF here and not your...
Yes. There.
Oh, okay.
Yeah.
I see what the hourglass is. Yep, I think that would work. Congratulations. That is kind of cool.
Nice.
That is. It's nice and cool. And, you know, it would make, if you were forced, if somebody came up and put a gun to your head and said, you have to do the Fourier series of this thing, you could actually do it with this, right? Without dividing the triangle into different parts within a tile. Okay, very good. Well, unfortunately, that ain't going to work because you can't. I think we can all see this, can't we? Okay, wonderful, wonderful. Very good insight. Very good insight. Okay, let me go ahead now, and if there's no other questions on the homework, I will begin to share my screen and talk about POCS. POCS is fascinating, isn't it? So let's continue with let's continue with POCS, and I'll show you what we can do. So hopefully, yes. Can you see my screen?
Yes.
My PowerPoint. Yes, Adam.
On like problem 53, just like a quick note, just kind of like a sanity check to make sure that I was doing that correctly.
Okay.
On each of those, you can just start mailing with just either a circle or a square, and then just use rotation, scaling, and shifting.
Yes, exactly.
All that just to create your shape.
Yes. Yes, that was the purpose of that. That was the purpose of that. And it was application of like the shift theorem, and those two separated ovals would be the Fourier transform of an oval times a cosine. Remember, because you get an e to the j plus, you get an e to the j minus, and those add up to a cosine. Okay.
Also, whenever you take you have the rotation matrix in the time domain, and you convert that to the Fourier domain, is it the transpose of that rotated matrix?
No. Think about.
In the book, you had something that implied that, I think.
No, if you rotate if you rotate an image, you rotate its Fourier transform.
Okay. So there would be no transpose?
There would be no transpose. R is equal to R inverse transpose. Okay. So R inverse is equal to R transpose. R inverse is equal to R transpose.
Okay.
Which is R is equal to R inverse transpose, yeah. And you can think of that, by the way, with, I like to think of this in terms of, I like to think of this in terms of diffraction. If you've done antenna patterns or propagation of Fourier optics, if you have an aperture, an antenna with a certain distribution here, your far field is the Fourier transform of this aperture. Have you seen that in antenna theory at all? Okay, and so just think of the geometry. If you have an aperture and you have the far field, which is the Fourier transform, what happens if you rotate the aperture? You're going to rotate the transform, aren't you? Right? It just makes sense that in propagation that you would rotate the far field, which is the Fourier transform. So rotation in one domain is exactly the same as the rotation in the other domain.
I brought that up because in the book you had stated that like x of t, or something like you had written down an example where or transposed in the,
yeah, could you email me the page and equation and I'll check it out. It could be a typo.
Okay.
Yeah, by the way, the champion on typos is David. He sends me one every day. I'm I'm getting embarrassed with all the typos that he's found. But such is life, right? Okay, this is what we did last time. Remember this one? We applied POCS to signals that were both bounded. Let's do this. We applied POCS to a signal that was bounded and had a fixed area, and then we went back and forth. We first of all made sure it was bounded, then we made sure it had the right area by slipping that down, then we bounded it, and then we summed it, and we bounded it, and we saw this iteration eventually converge to this signal, which was 1, 0, 1. And you'll notice that this thing is bounded between 0 and 4, and plus it has an area x1, x2, and x3, which is equal to 2. So this worked out to be very nice, and is an illustration of POCS, a very simple illustration of POCS. Then we went on to get another lemma. The lemma, the first of all, the POCS, the main idea is if you had two intersecting convex sets, you always intersected to a point in the intersection of the two convex sets. This generalizes to the case where you have three sets that intersect at some sort of point. And here we have three convex sets. We have this line. We have this line. We have this C2, which is, I don't know what that is. That's kind of maybe a bird's eye view of a boat. And then we had this oval over here. And those are three convex sets that intersect at a single point, which is right here. Now, we always iterate and converge to a point common to all of the sets. And in this case, we are going to always converge to this point, since this point is the only point in the intersection of the three convex sets. So no matter where we start, we're going to end up at this point. Again, the only intersection point of the three convex sets. And as we said before, it doesn't matter where you start. You can start down here. And if you start down here, you still converge to here. So we ended up with this example last time. We talked about von Neumann's alternating projection neural network. Here's the one that we didn't spend too much time on. Alternating POCS among two non-intersecting convex sets will converge to the point in each set closest to the other. In other words, given any two convex sets that don't intersect, there's a point in this set that is closest to all of the points in the other set. This point is closest to, what's the closest point in this set to this set? Well, it turns out to be here, right? And conversely, what's the point in this convex set that's closest to all the values in C1? Well, it's this point. And interestingly, in a limit cycle, if you get stuck in this limit cycle, you get to this point and then you will project over to this point, then we'll get here and you will project back. And so the POCS iteration actually breaks into a limit cycle. It oscillates asymptotically. You never converge, but you asymptotically bounce back and forth between these two closest sets. And that's kind of cool. Now, unfortunately, with three convex sets, nothing really exciting happens. Well, it does. There's something which happens in that it depends on your order of projections. Here we are projecting from, in this order, we're projecting from 1 to 2, from 2 to 3, and then from 3 back to 1. Do you see that? And if we keep on doing that, we will break into this limit cycle. We do break into a limit cycle, except it's of period 3, right? Because we get here, and what's the closest point here? Well, it's here. What's the closest point from here? Well, it's here. What's the closest point here? Well, it's here. And we break up into a limit cycle, which goes back and forth among those convex sets. And unfortunately, the order of the projections determines what that limit cycle is going to be. So let's go through another projection. Instead of going from 1 to 2 to 3, which is the solid line on the left, we're going to go from 3 to 2 to 1. Does that make sense? And if we go to 3 to 2 to 1, we get this pink dash line here. And we can say that pink dash line is definitely different than we went from 1 to 2 to 3. So we do get a limit cycle, but the limit cycle is not unique. And if you get to higher numbers of convex sets, it even becomes more complicated. Can you see that? So you get a bunch of limit cycles. So what would you like to do in such cases? Let's think of this from an engineering point of view. If you would like to do something with this, projection, what point would you like to do as a best compromise? You kind of like to have a point. You'd like to have a point here, which is in some sense close to here, and in some sense close to here, and in some sense close to here. So you'd like a point which compromises the distance between the different sets. That would be a good engineering solution, wouldn't it? And there is a way to do that. And what we're going to do is we're going to choose the point that minimizes the root mean square error, of all of the projections, the RMS value. And this is as follows. Here's a 1, 2, 3 limit cycle. Here's a 3, 2, 1 limit cycle. Oh, my point here is that 2 of the sets can actually intersect here, right? 2 of the points can intersect and you still have this problem with different limit cycles. I should have put that in before talking about the RMS. Do you see that? 2 of the sets can intersect, but you still break into a limit cycle. Okay, so here is something called simultaneous weighted projections. Simultaneous weighted projections. You start with an arbitrary value of y. So you start with any value that you want to, and you do the projections onto C1, C2, and C3. Now, don't forget, we're in a vector space here, right? So all of these values are vectors. Every point in the space is a vector, right? And what we can do is we're going to take the average of those vectors. This is the center of mass of the vectors. Does that make sense? We're going to take this vector, add it to this vector, or add it, I'm sorry, we're going to take this point, we're going to add it to this point, we're going to add it to this point, and then divide by 3. So we're going to take the average of those 3 points. When we do, we get a new point. This is the average between this point, or I'm sorry, not between, but among. This is the average among this point, and this point. We good? Guess what we do next? Do the same thing. We now take the average of these new points. We now take the average of these new points. And the average of those new points is even going to give us a, I'm sorry, okay, we're projected here. I'm sorry, here's the new points. We're going to take the average of these new points, and this new point is going to give us a new average. This new average is here, right? So the point is, here's what we do. We take the projections, we average them to get a new point to start with, and then we repeat. So we take the projections onto all the convex sets, we average them, and then we repeat. So it's an iteration. And the question is, if we keep on doing this, what do we converge to? We converge to a point that is the best root mean square value of the distances between the different convex sets. Now, this technique can be extended by weighting the projections. Maybe you have C1 here, and maybe C1 is a constraint that is twice as important as C2. And maybe C1 is twice as important as C3. So we would probably choose weights of 1/2, 1/4, and 1/4. Notice that the weights add up to 1. The weights add up to 1. And if this one is twice, if this C1 is twice as important as the other two, instead of just adding up the vectors, we add a weighted version of the vectors. And then we will get a solution wherein the solution as is going to be closer to C1 because C1 is more important than C2 and C3. This is a classic Pareto trade-off. You have a number of, I don't know if it's a Pareto trade-off, come to think of it. No, it's just a trade-off where you choose the best result in accordance to weighting. If you have no preference of the weightings, you just use all of the weights equal to the same, 1/n. So you add them up and divide by 3 in this case, right? You add them up and divide by 3. So you multiply them all by 1/3. Okay. If you did not, if C1 was twice important, you would take the projection onto C1, multiply it by 1/2, and the other two multiply it by 1/4, and that would give you a weighted average in terms of the results. So you can get weighted averages and useful results even when your constraints are not intersecting, even when you have 3 or more. So these are very good. I had a PhD student that generalized this to another technique for generalizing, but I'm going to add that on maybe. I don't know, maybe I'll talk about it if we have some time. Let's talk about some applications here. Here's a very interesting problem. And this was a problem considered open in electrical engineering and optics of all places for a long time. The problem was as follows. We have a signal that we know is band limited. We have a signal that we know that is band limited, but we're missing a portion of the image. We're missing a portion of the signal. We don't know what is in here, right? So we have the tails, but we're missing what is in the middle. Now, what are the convex sets here? The convex sets are all signals with identical tails. We know that all signals with these tails, with the tails that are shown, form a convex set, right? All of the signals with the tails form a convex set. We also know that the signal is what? Band limited. Correct? So here's what we're going to do. We're first of all going to start out with our signal with the known tails. Let me make this big because I think that the red writes on this better than the black. So we have something that looks like this, right? But we don't know what this is. We don't know what this is, right? This is a function of time. So what are we going to do? We're going to Fourier transform it. And when we get into the Fourier transform domain, this thing is going to be something that looks like this, right? It's not going to be band limited because we have some sharp changes here. We have some sharp changes. And anytime you have abrupt changes, that corresponds to high frequency. Well, so here's what we're going to do. We know it's band limited. So we are going to take this thing and we're going to run it through a band. We're going to run it through a low pass filter. And we're just going to keep the middle of it. Does that make sense? Then we're going to inverse Fourier transform it. I don't know what the inverse Fourier transform looks like, but it might look like something like this, right? What's wrong with this as a solution? It doesn't have these tails, does it? It doesn't have these tails. So I'm gonna discard the tails that I have here. And I'm going to stick in, I'm going to keep the middle part. And I'm going to stick in the tails. Does that make sense? So let's do what I'm doing here. Going from here to here, I'm projecting onto the set of band limited signals. Going from here to here, I'm making the signal band limited. Now I'm going to go back to the time domain and stick in the tails. That's projecting onto the set of all signals with these as tails, right? And then I'm going to do the same thing again. I'm going to do another Fourier transform. So I'm going to project onto band limited signals. I'm going to project on the case where there's all tails, or where the tails are known, project onto the band limited signal, going forever. And I'm going to keep doing this. And this is a projection between two convex sets. The set of band limited signals with a known bandwidth and the set of all signals that has tails that look like the known portion of the band limited signal. And so hopefully POCS should converge to something that looks good. Does this make sense? So if we do that, we get, you can see the animated graphics here. We can see the animated graphics that just, it's a little animated GIF that just keeps repeating. And as you can see in the upper right here, this was the signal that I took this signal from. That was the signal that I took this signal from. And you can see that the reconstruction of the signal kind of in this area kind of resembles what's happening here, which is kind of cool. So we have reconstructed the missing middle using the concept of POCS.
Is the picture on the right, that's what it's like before you cut out the middle, and then
yes,
after you cut out the middle? Okay.
Yeah, this is one of the cases where I knew the solution. So this was this was known. So this was my band limited signal, and I took this and I threw away the middle to get the initialization for the POCS. And so because I know the solution, my POCS should converge to the known solution, and it does a pretty good job of doing it.
So I guess we've talked about if you started with a different point, though, you might have ended with a different point. Here you assumed that the thrown out portion was 0. What if we made the thrown out portion 1?
It would still converge to the same point, because if you remember, identical middles corresponded to a plane, right? I don't know if you remember. This is kind of identical middles, except it's identical. This is my kind of X, Y, and Z. And this was the space of identical middles. So the space of identical middles is the space of identical middles is a plane. This is an identical middles. It's identical tails, isn't it? This is identical tails. The set of band limited signals is also a plane. And in this case, the set of band limited signals comes out, cuts through the plane here, and the convergence is in a single point.
Dr. Marks?
Yes.
I think I might have missed this while I was trying to draw those graphs, but I'm not understanding, like, what are the convex sets in this case? Because it sounds like you're just doing like Fourier manipulation, but what are you projecting on? Like, what's the,
okay, let's go back one. Number one convex set is the set of all signals that have these as tails. Mm-hmm. That forms a convex set. Number two is the set of all band limited signals. So there's only two convex sets here. The set of signals with identical tails. And so if you're a member of this set, you can have wiggles in the middle and wiggles on the top and wiggles anywhere you want to. Band limited signals means that you're limited to signals whose Fourier transform lies between a minus bandwidth and a plus bandwidth. It has to be 0 outside of that interval.
Okay, and so on the simulation, or I don't know what you call it, what you had on the next slide in the GIF, what's the so the number you did, the number that keeps going up, that's the number of projections you're doing. So does that correspond to just how many times you went through that process, basically?
Yes.
Okay, yeah.
Yes, went through the iteration. That's one entire loop through the iteration. This is after, you notice that the tails aren't changing here, are they? So this is after the tails are added in. I guess the point is that I could have stopped and showed you, well, this is a picture of this. It's a picture after I've added the tails.
Okay, so what that right there is one iteration.
That would be one iteration. That's correct.
Okay, cool. Thank you.
Okay, very interesting result, the Popoulas-Gershberg algorithm. It attracted a lot of attention when Popoulas and Gershberg individually came up with this result. And they battled back and forth for a while of who was first, and Popoulas dominated that debate, and so he got his name first. But Popoulas and Gershberg did the same thing. They came up with the same result. And plus, Gershberg's proof was not very definitive, whereas Popoulas's was. Popoulas was able to prove this iteration always converge with something called prolate spheroidal wave functions, which, yeah, and it's a prolate. Remember, we've seen prolate spheroids. There's a wave function associated with them. I guess is the way electromagnetics bounces off a prolate spheroid or something, but they prove very useful in signal analysis and things such as windows. But he proved it. Popoulas proved that this algorithm converged. This is very intuitive. I've just presented this to you from a perspective of POCS with a little bit of hand waving. I think you can see that it has two convex sets. And we always seem to get this, this result.
Okay. So how much, how large of a gap can be?
Okay, we're going to get into
in?
that next. We're going to get into that next. You remember I talked to you about calling up your mother on an old telephone where they charged you per minute and you just had a little part of the conversation and you were able to hang up because the signal was band limited and you knew the tails, right? You talked to your grandmother, you didn't know the tails, but at least you knew the beginning of the conversation. And so it turns out to be a POCS problem. It's exactly the same. It's exactly the same, except what you know is that you have a signal, and here's you talking to your grandmother up to time t, and you know that this is a band limited signal, right? So here's your convex number one. That's all of the conversations that your grandmother would give you up to time t. And then we have to have it band limited, and we could apply the previous Gershberg-Popoulas algorithm to hopefully extend this out into as long as you want. And I tell you something, mathematically, this works. But there's an old engineering axiom that in theory and reality are the same, but in reality, they're not. In theory and reality are the same. In reality, they're not. And one has to go a little bit deeper, and one gets into a problem called ill-posed or ill-conditioned. We talked about this previously. Do you remember me looking at balancing a pencil on my finger and saying that all of the forces, according to Newton's laws, add up to zero? So if I let go of the pencil, then that pencil should stay exactly where it's at. But it doesn't, of course, because a little bit of variation in my model makes the model useless. And it turns out the same thing is true for the Popoulas-Gershberg algorithm. Let me give you an example. It's a classic example. Yeah, here's the example. Again, the idea if you have a block and you put it on, you have the block pushing down with a force, and you have the table pushing up with an equal and opposite force, and the sum of the forces is equal to zero. And in order to get motion, you have to have a force acting on a mass. And since your force is zero, there's no action on the mass. We have the same thing here. You have the pencil pushing down at a certain force. You have your finger resisting this force, so the sum of the forces is zero. So therefore, if you let go of the pencil, it should stay exactly where it is. It doesn't do that, of course. And it's because the problem has become ill-conditioned or ill-posed. Here is a classic example. Okay, let me give you, here's kind of the background. You know that if you have a matrix which is singular, that you have a determinant of zero, right? If you have a matrix which is singular, that has a determinant of zero, and you can't invert that matrix, can you? You can't invert the matrix. It's like dividing by zero. You can't do it. But what if the matrix had a determinant of like 10 to the minus billionth. That's almost 0. And if you if you have y is equal to epsilon times x, where epsilon is almost 0, then when you invert it, x is equal to y over epsilon, right? This is inversion of this equation to find x. Well, look at this epsilon. Epsilon is equal to 10 to the minus, I don't know, every how many zeros you have to put here. So epsilon is almost 0. So you divide by epsilon. What happens to epsilon? It's a very, very small number. And if you add epsilon, if you do any sort of variation on epsilon, you add a little bit of noise. Even round off error, right? If you have 10 to the minus 10,000th, that's not going to be in the precision of your computer. You're going to have some sort of round off error. So if you add a little bit of noise, this inversion becomes crazy, correct? We see the same thing with matrices. Here is a matrix. Here is a matrix, and it looks very nice, but it does have a determinant which is very, very close to singular. It's not totally close to singular. Its determinant, though, is very, very small. And here is the inversion of that matrix, 10 to the 8th times all of these numbers. It looks like a very, very simple operation. However, and guess what? If you multiply this ill-conditioned matrix by 1, 1, 1, 1, 1, you get this result, okay? And if you take this result and you multiply it by A inverse, these two vectors are exactly the same. If you multiply this vector by A inverse, you get the result that you want out, 1, 1, 1, 1, 1. So this is great. It looks like it works, correct? But let's just add a little pinch of uncertainty here. And this is really amazing. We are going to keep the same exact vector here, except that instead of 3.9246, we're going to, or 3.9245, we make it into 3.9246. So the only thing we're changing from this vector to this vector is this number in the 4th decimal place, from 0.5 to 0.6. Look what happens in this matrix, which is almost singular, if we make that itty-bitty change. All of a sudden, the results are not the desired 1, 1, 1, 1, 1. It's not even close to 1, 1, 1, 1, 1. It turns out to be this. And one of the elements, for example, here is 23,000. It isn't 1, it's 23,000. And this is an example of a system which is ill-conditioned. You add just a pinch of uncertainty to it, and that pinch of uncertainty totally screws up your model. Totally screws up your model. And this, in this example, ill-conditioned is illustrated by a matrix which is nearly singular. It's nearly singular. So we see that there's lots of problems in engineering that are ill-conditioned, that a little bit of uncertainty in the design, if it's an inverse, will give you a terrible result. And it makes sense. If we go all the way to 0, if the determinant is 0 and it's singular, we can't invert it. If the determinant is 10 to the minus billionth, well, yeah, maybe we can invert it, but we got to be careful. We got to be careful. We get things which are amplified. So this is what happens. This is the mathematics between what happens when we try to do this interpolation. By the way, if you're familiar with eigenvalues, you can determine the condition of a matrix by taking its maximum eigenvalue over its minimum eigenvalue. This is something called the condition of A. And if the condition of A is a really, really big number, the bigger this is, the worse your problem becomes. And if you have a singular matrix, the condition of A becomes infinite. So if you have the condition of A being a very large number, you got problems. You better watch out for any noise or any uncertainty that enters your model, because it's going to screw you up. So what's the takeaway here? The takeaway is that if we have the beginning of a record, give me a good record. Give me a good recording. I've been listening to Leadbelly. And he did a song called Goodnight Irene. And Goodnight Irene is important because Goodnight Irene was #1, a Leadbelly song, which was written, and it was performed by a group called the Weavers, and that was #1 when I was born. So Goodnight Irene by Leadbelly is really cool. He got the name Leadbelly because his last name was Ledbetter. And I'm sure that somebody asked him, what's your last name? He said, my last name is Leadbelly. And it probably came across as Leadbelly. Okay, so here we have it. This is the beginning of Goodnight Irene by Leadbelly. Here's the end of Goodnight Irene by Leadbelly. Well, it turns out that the bigger this process becomes, the more ill-conditioned it becomes. Meaning that if you just change this just a little bit, just like up here, if you change this result just a little bit, you might get a result perfectly, which gives you your grandmother or the rest of Goodnight Irene. But if you change this a little bit, you're going to get something that goes like this. You're going to get something that goes crazy. And oftentimes this condition is, if it's greater than the precision of your computation, forget about it. You can't analyze the problem using the precision of your results. So mathematically, in the absence of all noise, yeah, you can do it. But that's not the way reality works. In reality, we always have noise, we always have a degree of uncertainty, and the process becomes ill-conditioned. However, if you just miss like a minute, not a minute, but just maybe maybe a few milliseconds, you could probably come in here. Shoot, you wouldn't even have to do Gershberg's algorithm. You could just probably fill this in, couldn't you? If you just missed a few milliseconds. I always thought about it like missing a movie. If you just step out for a minute and you're not watching the movie anymore, you can come back and you can kind of interpolate from later scenes what you missed. But if you miss like, a half hour or 45 minutes of the movie, unless it's a really simple movie, you can't figure it out. So that's the problem with the Populus-Gershberg algorithm, is that our common sense is made whole again, because it says that we can't do a lot of interpolation. Many of you remember, or maybe historically know about Richard Nixon's tape, where the tape was erased. And there was Richard Nixon, the president, a former president, used to tape everything inside the Oval Office. And during the Watergate investigations, they subpoenaed the tape, and they found out that the tape was erased over, I forget, over 10 minutes. And of course, if the Gershberg's Populus algorithm worked, that would be no problem. You could restore it. But the problem is totally ill-posed. It isn't going to work. It isn't going to work. Okay, let me check the time here. I think that our time is probably up. It is. In fact, we're a little bit over. So with this, then, let me ask you if there's any questions about the Gershberg-Populus algorithm, which is probably historically I guess the first historic application of POCS was with von Neumann and his alternating projection theorem. But the first popularization of the POCS was the Gershberg-Populus algorithm, or the Populus-Gershberg algorithm. And we're going to look at other applications of the of POCS that are more understandable. Specifically, we'll look at generation of images from their projections using the idea of projection onto convex sets. We'll look at some pixel resolution, and then look at some problems of places such as oncology, imaging in astronomy, and other places. So that's what's in the future. By the way, for your final examination, I'm going to be asking you to do something in POCS. And I'm gonna leave you with an open field in what you choose to do. So you might start thinking about it. And I don't think, maybe if you're just following the lectures and just keeping up, we're not to the point where you can probably do something interesting with POCS. But keep it in mind as we begin to do lecturing on it, because POCS is a difficult thing to give homework on. Okay, it's a difficult thing to give homework on. So I thought for a final examination, I would just give you a project in POCS, and you can go bang out some stuff in MATLAB or something. Any questions at all?
Is the final exam, is it not going to be oral then? It's going to be like more like a project?
No, we will have a second oral exam, which is kind of the second midterm, if you will. And then we will have the project, which is due.
Do you have an idea of what the due date might be for those?
Yeah, I will probably have the due date as the date which is scheduled for our final exam, which I don't know what that is.
Okay.
Okay. Okay. Thank you, gentle people.
Dr. Marks?
What'd I do?
Oh, no, I just had a question.
Oh, okay. That was a joke. That was a joke. And you're right. I am paranoid. So, okay.
So on my earlier question, actually, with do they converge to a single point? And you said they do, even though they're both a
okay,
plane.
that's a good point. I've reconsidered. I'm not sure that they do. I'm pretty sure that they do. I can't prove it, but I have a good feeling that they do.
Okay.
Do you have some alternate evidence?
Well, I was just thinking, like, as you know, if you have two three-dimensional planes, they intersect in a line.
Yes.
But these are very high dimension planes.
They're very high dimensional. And the question is, how indeed do they intersect? We know though, that if we have a band limited, okay, you go back to the Taylor series. Remember the Taylor series? And we argued this interpolation problem from the Taylor series, that if you took a point at some value and did all the derivatives, then you could generate the signal everywhere. Okay, well, it is true that all band-limited signals are analytic. All band-limited signals can be expanded in a Taylor series that converges everywhere. Take my word for it. So with that being the case, then every point in that band-limited signal, in theory, without any noise, which you can't do in practice, is going to converge to that band-limited signal. So the band-limited signal is already defined even without its interior. So that makes me think that in fact, I would give you odds if I were a betting person, and I'm not, but I would give you odds that it just converged to a single point because of that fact.
So then the band limited plane is possibly a higher order than the tails plane?
No, both of them in continuous time are infinite dimensional. So, which is really weird, right? However, the Popoulas-Gershberg algorithm that I showed was in a finite dimensional discrete space, right? So, you know, there might be something there. But I do think that the tails totally do determine the band limited signal in the continuous case. So that leads me to believe that there's only one solution that one gets using the Popoulas-Gershberg algorithm. Oh, come to think of it, Popoulas proved that. So I will go back and say 100%. Remember I said Popoulas proved this using prolate spheroidal wave functions? The proof is in the book. And if you wanted to look at the book and look at the proof using prolate spheroidal wave functions, which I think is in the chapter before this, you will find out that that proof shows that there is a unique point of convergence. So yeah, we're good. Okay. Sorry I didn't have that trickling off my fingertips, but it took me a little while.
Dr. Marks?
Yes.
So since we'll be doing like a project on POCS, does that mean that the oral exam will not include POCS?
No, I might ask you some general question about POCS.
Okay.
What I'm interested in, and I think you know this from the last examination, is your general feel for things. I don't want you to come out of here with a bunch of equations memorized or stuff. I want you to be able to come out of here and think, because when you get away from academia and you're out in your job, it's going to be that as opposed to the memorization of equations, which is important. You're going to go, for example, oh, look at that problem. Oh my gosh, that was POCS. Oh, I remember POCS. Let me go back and review it. So you'll know where to go to look for it. Or if you see some sort of signal and you say, oh, you know what? How do I sample this? Oh, I remember the multidimensional sampling theorem. I can go back and look at that. and you can come back and you can brush up on it. So that's what I'm interested in, is pounding in these general ideas. That's the reason most of my lectures are kind of geometrical and I think hopefully intuitive, and they also allow rigor where it's needed. Okay. Okay, I guess we're done. Any other questions? Okay, thank you, gentle people. We will see you. We will see you on Tuesday.
Everyone.
Okay. Can I stay on?